Draft physics video. Yes, on gravitational lensing again. I'll read a comment, maybe comment on a article I just read that seems rather preposterous, and the general subject of the fact that there's really no gatekeepers to scientific integrity. It's getting published means getting published in some commercial magazine, generally speaking, and certainly one protecting an interest group, besides just protecting science from frauds or bad science. So there's really no gatekeeper doesn't have an interest. And this is really a bad circumstance, and it's kind of illustrated by these very arguments in the sense of the most famous lensing experiment was this Eddington experiment, and that was sort of in the guise of supposed to be connected with this institution that cares about the integrity of science. And ironically, the institution was hugely prejudiced in favor of Newton, and was tended to be kind of obnoxious to any challenges to Newton. And Eddington snuck his way in, so to speak. Got in and then changed affiliations. Okay, he became a supporter of Einstein and was an aggressive supporter of Einstein in doing his experiment. And so you have this huge conflict of interest that didn't, no bells went off, no anything. And today, still the experiment is mushy at best. I mean, we don't even have the data that's published. Why don't we have the slides? High resolution images. They're glass slides. I mean, why aren't they on the internet? Anyway, it just all reeks, and it's very discouraging that people won't even concede that they got to play a better game than this. Science needs to play better science. This is really bad science, and it's been bad science for a long time, 100 years of sloppy, where they really don't. There's no critical evaluations. It's just whatever gets published is published. No one seems to pay any attention to detail, and there's no test that had to be passed in any sense besides you fooled somebody at a magazine. That's all that's required. Alright, so hubris hat stuck. Hack stuck. Anyway, your argument at 613 that the other observer wouldn't see the star isn't quite correct. He wouldn't see that ray which is shown to be bent, but there are other rays leaving the star in all directions, and one of them is bent more slightly further away from the sun so that it reaches the observer. I think that just negates the argument that, yes, clearly there's points. I mean, if you were to think of a star as a light bulb, it's really made of a bunch of light bulbs inside of the light bulb, a bunch of little point sources, and each one is radiating from all directions. So it's not, it's a light bulb inside of a light bulb inside of a light bulb kind of thing. So there's lots of different angles that light's leaving at. But the simplest argument I can make is this. So when I do this, let's see, if I focus on the lens, that should focus my eye. Well, I'm not sure about that, but anyway, you can sort of tell this whole magnifying thing means that you can't see what's missing of my face. You'll see the part that's sharper, and everything else is gone because the lens is obscuring it, so it's gone, and you can't see it from any other place, so it's gone. So only the magnified bit is going to be visible. So I'm just saying the loss is real, and it leaves the lens at, obviously at these huge distances the lines are thought of as parallel, but they're not really parallel. There is an angle, and over light years of distance, millions or billions of them, that small angle is going to add up to a rather big hunk of space that you're blind to because of the lens. So I don't think you can get around that argument that anything inside the lens is hopelessly unobservable if you're observing something getting lensed. If you're seeing something magnified, then you're not seeing everything around it by rule. And the other rule would be is that anything closer that moves into the field, like with this magnifying, something moves into the field, you can't help but see the distortion. So if I move my finger in here, it's going to distort whether you like it or not. Even if it's out of focus, it's going to create a source. And like I said, focus is irrelevant. You can't make that disappear. And so none of these lenses ever do that. Nothing close ever obscures one of these lens views. Every single lens doesn't have anything behind it close. That's how it's worked out, right? Every single one can't possibly have anything bright close behind it. Because if it did, it would magnify that, whether it liked it or not. And if it was out of focus, it doesn't matter because the light's going to obscure your vision. Alright. Probably enough. I mean, you know, these lenses don't really have a focal length because they're so long anyway. But anyway, you know, in the whole shape of the lens argument, we'll get into that one. Alright, reaches the other observer. Note that a gravitational lens is not like a convex lens, but more like a concave lens. Well, I've sort of made that point in previous videos. I drew it as a star almost, a four-pointed star. But the problem with that is normal light reflection rules don't even allow that lens to be made as a lens because light will reflect off the surface rather than diffract into the surface. So it can't even work as a lens if you manufactured it one. You know, so a gravitational lens obviously won't have the same refractive index as a glass lens because it's not using diffraction to bend light, it's using bending, you know, which is quite different. It's not a surface phenomenon, it's a through the gravity phenomenon. But the point is that you could still illustrate it by how much the light is turned. And the truth is that these huge gravitational lenses would have very strong gravity. If they're capable of lensing light at that location, then they have to have some other location where there's really intense gravity, and it would be able to bend light in eccentric angles. Okay. But this sentence is just totally unacceptable. Okay. It's more like a concave lens with a variable curvature proportional to 1 over r. No square law. I don't understand how you could type that. You can't undo the rules of gravity. Right? Gravity's an inverse square proportion. The gravitational lens, by definition, has to obey the rules of gravity. That means it has to be constructed out of the inverse square law. You can't just say 1 over r. How do you get rid of the fact that gravity doesn't work any other way than the inverse square? There's no 1 over r gravity. It can't be made. You can't give me a theory for how the gravity isn't obeying the inverse square law. So I don't know why you type that sentence. You'll have to explain that one. Some compare it to the foot of a wine glass. Again, that wouldn't be 1 over r. The foot of a wine glass would be the inverse square. So, wrong again. This property guarantees that some light rays from the star is bent just right to reach the second observer. I totally disagree. There's absolutely no guarantee. And Yeah, no, I don't buy the argument. And regardless, as you just said it, some light, so you would have a noticeable dimming of your image if some light doesn't get to the same observer. So I just don't buy this argument. Another consequence is that the lens must produce mirror images inside the Einstein ring of objects which are outside of the Einstein ring. I don't know what theory dictates that, so I don't know. Clearly those don't exist, so you're right, and then maybe that's a problem, but I don't know why there has to be more than one ring. This is not visible in those images, and in my opinion, the strongest argument against lensing. Well, I think the inverse square law is a stronger argument that such a lens couldn't reproduce spherical symmetry, couldn't reproduce galactic shapes. It would distort highly. Furthermore, even if there is nothing behind the lens to produce a bright Einstein ring, it would produce a black Einstein ring, which would be detectable. So I've seen that speculated about black holes having these rings, where one of them is a black ring. But yeah, I'm not sure exactly what the theory is behind it, so I can't say. With mirrored images inside. Alright, so I'll go through a couple of the things. Alright, there's lots of problems with the lensing images. First, most of them are blue, and that's never been explained. Why are the lensed images blue? They're supposed to be things really far away. They're always things really far away. 9, 10 billion light years away. And those things are supposed to be predominantly red shifted. So why are they coming up blue when we lens them? I haven't seen any theory on that. Okay, there's just so much stuff to... Alright, so I'll just do this real quick. These are sort of arguments that I've made that I think are solid. And also a new observation I had about, somebody said, well, how do I explain those classic images of the big giant Einstein ringy kind of thing, the smiley face and that stuff. And I remember now I saw a 60 symbols video on these emissions from galaxies of protons and electrons, huge, insane amounts of energy from like some sort of whatever happens to the dense matter inside the center of the galaxy. It apparently emits this huge amount of matter, and you can only see it it only creates radio frequencies, so they can image it using radio telescopes, and it's this massive emission, and it sort of comes out of the galaxy like this. It comes out both directions, and as it goes out it starts to spread. And I just recall seeing the obviously every image is always an enhanced image, but I remember seeing the image of it, and when you think about it, it would explain if that happened and there was a galaxy in the way of that emission, it would get pushed and spread, by the emission quite easily. It seems reasonable to speculate on such a possibility. Alright, so this is what 2 years ago, this is how I drew a gravitational lens. Essentially, it's got this, this is the line that you have to deal with, and it's unyielding in terms of there's no way you can make there's no way you could take an image, say, these lenses are huge, we're talking about light years across, and there's no way you could take a big hunk of a blob this size and image it with this lens, because the strength of the gravity here is so much stronger than the strength of the gravity here. I did just a little bit of math, and the Earth has 10 meters per second gravity on its surface, and just 3 Earth diameters away the gravity is already down to 0.2 meters per second. So it's like 2 feet a second versus 10 meters a second. Just 3 diameters away from the Earth. You know, 1/8 of the distance to the moon, and you're already down to 0.2. So you know, it's a huge difference in the amount of gravity with each step you take in any direction. It's a huge difference in the gravity. Huge difference in how strong the lens is. So it makes none of these images make any sense. Alright, and the other thing I pointed out was the lensed images are always around galaxies facing the circular part. So they're flat and they're coming at you this way. And then they show the lens, that would be the lens. And as I've pointed out, the galaxy this way, you're going to experience so much more opportunity to be in the gravity. So when the lens is flat this way, when you see it this way, that means the light is passing this tiny distance through the galaxy. So it's coming this way, it goes this tiny bit through the gravity and then out. Where if it had to go across the galaxy this way, it would be in the gravity 1,000 times more time, plus it would go closest to the center. So if you're going across the light, so if the light was going across this top of the galaxy, it would go, look, the distance from the center is huge here. The distance to the strongest gravity near the center of the galaxy, it would be closest to that. And so there's a much higher probability of bending. I mean, thousands of times higher probability, maybe 1,000,000 times more probable that light will be bent coming over a galaxy this shape than facing you this way. 1,000 times, more than 1,000 times more probable that you'd bend light under that circumstance. And yet not one single image of a galaxy lensing in that configuration, the strong configuration. So I'd say that's a pretty glaring, unexplained truth. Yeah. Alright, so let's see if there's anything else I wanted to get to. So the blue thing, you know, I did do some research on, well, I didn't do research deliberately, I just happened to fall into it. A whole discussion on the fact that, you know, although digital cameras are really, you know, we have this great technology, 2 problems have happened in terms of the technology. First, they've compressed telescopes by using, you know, reflective mirrors and stuff, and so they're more vulnerable to distortion, and so that's really bad for measuring lensing because you're talking about a tiny difference in location. And the other problem is that digital sensors don't have fine enough pixel depth to be able to image the images, you know, without, it makes it jump into a location. So if something's coming in between 2 pixels on the sensor, it forces it into one or the other. So it can't ever go to the middle position. So the resolution isn't high enough on digital sensors. And so that, I figured there's got to be ways around that, and Hubble obviously must use mechanisms to get around that. But it is sort of a liability of doing this in any kind of amateur way. You know, you really do, you know, the amount of angular difference for, say, solar lensing is 0.0002 degrees. I mean, it's a tiny percentage of a degree that the object is moved. But I would argue that obviously doing this from the ground is stupid. because you're totally dependent on comparing two images taken 6 months apart that have little hope of being from the same distance and having the same resolution. So that's a fatal flaw, in my opinion, for doing something this precise. So doing it from space is the only rational thing to do, and clearly they have all this technology they've put into space. There's no reason why they can't just track a star that they know where the sun is going to go right underneath that star from that position, and they just could track the star and then track it based on the rotation of the satellite. You know, don't track it by looking at the star and staying centered on the star. Focus on other reference points in the field that don't move, that are further away, so less likely to be moving. Less likely to be moving relative to you, however you want to say that, changing position in any way. Anyway, or just track it based on movement. So that could be an algorithm of what your movement's going to be, and so that would always be a constant adjustment of the tracking. So as long as you have a constant tracking, and then just track that star, and then just wait for the sun to go right past it and see if the star moves. Now, if it was scatter alone, see that's the other argument with scatter, is sort of an interesting thing I hadn't thought of. Scatter is not likely to change the position. Scatter will create something like an Einstein ring, but scatter won't change position. But what it will do is make something bigger and fuzzier. So it's kind of like in a fog, lights, or even the whatever they call that, the harvest moon or something, or even in the sun, in the autumn when it gets really big. That's just scatter through the atmosphere, and it just makes it seem big when it's not that size at all. So that scatter. Now the trick is that they use other non-visible light imaging to verify lensing. And I think that's what that NASA scientist is basically talking about in terms of blaming it all on scatter. It's all these other experiments are using radio waves or some other photon. Scatter will fool them because they're not resolving an image. So they will get light diffracted around an object by the scatter, and so they'll say, hey, it got here too soon, the radio waves came back too soon, and they went, they bent around the sun. Well, they didn't really bend by gravity, they bent by scatter, and you couldn't tell the difference with a radio wave because you're not resolving an image. So without an image to resolve, you can't tell the difference between scatter and lensing. There's a more precise way to say that, but anyway, it basically eliminates the evidence from radio waves or microwaves or any non-imaging photons as evidence of lensing, because if you're not doing the imaging thing, then yes, of course there's going to be diffraction through the atmosphere of almost any body in space. Has some kind of atmosphere around it, charged particles, whatnot. Alright. Okay, so I did that. It's probably enough. Alright, so let's go to this article. And I know you people aren't really players here in any kind of serious way, but I'll leave a link below to this article, and if somebody can explain how this can have any meaning at all, how this is at all a credible piece of garbage, I'd like to be edified. I did click links, I tried to find more information, and it was just the same mush. It was just nothing coherent. So the story is basically saying astronomers for the first time predict a replay of a star's violent death for the first time. So the idea is that there's a supernova way far away in a distant galaxy. Assuming. I have to just assume, because what else can you do, right? And whether the whole galaxy is being lensed, you can't even tell from the way they're saying this, or whether just the star is being lensed. But anyway, so there's a supernova, and it shows up as 4 dots in one of these gravitational lenses. Now, of course, the lens doesn't obey any kind of symmetry. I don't know how they're drawing the gravity that's creating this, but obviously, if you have a complex gravity field, the odds, it's just a matter of odds of saying, because the gravity competes with each other from different objects, so that it ends up with 0 gravity in some locations, like halfway, not halfway, but like 80% of the way to the moon, there's a point where there's no gravity because of the balance between the moon's gravity and the Earth's gravity. So there's absolutely nothing. There's a point where there's just nothing. There's no, if you put something there, it wouldn't go to the moon and it wouldn't go to the Earth because it's being neutralized. It's being pulled both ways equally. And those locations are real. And every time they talk about a cluster or some other thing, they have to deal with that fact that this is the lens is a mess. And to be able to resolve 4 objects in a lens this messy, the odds have to be, four images of one thing in a lens this messy, the odds have to be astronomical. And then this article is basically saying that, okay, so there was these 4 images, right, of the same supernova, right? So these are 4 images, and there's no explanation for why, like, these do, you would assume there was some arc to the gravity lens. So my argument would be, well, why wouldn't there be an image here, an image here, an image here, an image here, an image here? Why wouldn't there be a ring? What's wrong with the gravity here and here and here and here that it's not creating an image? Where did this gravity go that it doesn't exist and that it's not creating an image? These Einstein cross thing, I don't think, like I said, I don't even think Einstein believed in an Einstein cross. I don't know why they're naming it after Einstein. So I don't think Einstein said there's any such thing. There's a ring or there's nothing. You don't get to just arbitrarily say the gravity's enough here and the gravity's enough here, but not enough here, not enough here, not enough here, not enough here. Gravity doesn't work that way. It really doesn't. Alright, anyway. So, what they're saying happened here. So now they have, they have these images that obviously never have anything to do with the story. So first, I don't know what this has to do with the story. So the story is about a supernova, and they have this image. I've never seen a supernova explode this particular way before. That looks more like these jets that come off of galaxies, actually. But regardless. Then they have this image. Now, it only has 2 objects in it, and they're galaxies, not supernovas. So obviously this image is just a generic image of some generic lensing and has nothing to do with a specific case. So what they're saying happened is, alright, let me get to this. So there's these 4 images. Well, I can show you. So these yellow dots. Now the fact that they're yellow is interesting because most lensing images are blue shifted like the rest of this stuff. But clearly this image, I don't know whether you can see it. I wish they just posted the images. This looks like 2 galaxies merging here. They're affecting each other. So all of this can just be the stuff being pulled by that interaction between the 2 gravities. But regardless, these are the 4 dots that they say are the same supernova. And so I would ask the question, why isn't there an image of it here, and here, and here, and here, and here, and here, and here? How is this gravity not symmetrical? Why isn't it symmetrical? How does gravity become non-symmetrical? How do you make gravity non-symmetrical when that's exactly what it tends to do by even like Maxwell's equations? it's an obligation of the function. Alright, so anyway, getting to the point. So the story is basically saying that, okay, these 4 images showed up, then they disappeared a year later. And like 4 years later, from first notice, or whatever, 2 years later I think, a little blob showed up here, and they claim it was the same supernova in this new lens way out here, somehow this other lens, and it showed up 2 years later because it took a longer path. So the light traveled a longer distance and got bent more, which would have to be the case for us to see it. But anyway, and we see it way over here. So that's what they argue. So that they had 2 lensing events, 2 lens, and one of them is the object from 2 years later. So they're claiming that's a realistic possibility. Then, okay, so that sounds wacky enough, all right? The idea of saying somehow the same lens at a location 2 or 3 or 5 or 100 light years away is going to lens the same object. The odds of that happening should be astronomical. But anyway, so the weird part is the images don't verify what they're saying. They almost are, the images say it all happened, they disappeared, and then they all came back, all 5 of the objects. So in the original lens, somehow 2 years later they showed up again. It just doesn't make any sense at all. So here's the 2 images. So this one is from 2011, and there's no spots in these locations. And so here's the one, this is the one they say is the same thing. Way over here. Way over here. They're saying it's the same object that's behind this thing that's making these 4 objects. And they're saying somehow this one showed up. But the photographs indicate that when this one showed up, these 4 also showed up again. So they're saying they first saw these in 2014, then they went away. Now we don't have that picture. And then in 2015, all 5 of them showed up. That doesn't make any sense at all. I mean, if anybody can make any sense out of this, fine. Please help me out. But these images don't validate the story. Now, if there was an image of this dot and these 4 were missing, well, then this would fit the story. But these images don't fit the story. So it's garbage. It's rubbish, nonsense. So, yeah, like I said, and I went to the I guess you can call it a technical paper, but it isn't very technical. And they don't have anything here but the same image that doesn't demonstrate what's in the story. And there wasn't much in the story, frankly. So, it's like, who's the guardian of this? Who's watching to make sure people just don't make up crap? Well, anyway, and so the other thing I thought of, too, was just the fact that these are so different a color. It seems to me that they might be invisible in the 2011 photograph, which is slightly lower contrast. So let me back up. You can sort of see that the contrast is different. And there is a little bit less detail, sharpness. And the key to that might just be that these objects are emitting a shifted light, and this image filtered those images out. So they might have been in this image. It's just because of their status as being whatever they are, that why they're differently. They're obviously colored differently for a reason here. So they're obviously producing some sort of radiation that's different than these blue blobs. So I'm just saying that they didn't just, let's just assume they didn't just completely fake this image. So there's a reason why this one's yellow and this one's blue. And maybe the reason why they're not in this photograph is because this photograph couldn't see the yellow things, and it could only see the blue stuff, which almost everything else is in this little image, as you can see. So anyway, but yeah, this is, it's sort of to the point where, it's not a conspiracy in the sense that I don't think anybody's, I think there's got to be astronomers who know that they're just talking shit, that they're just really way out on a, let's just make it up limb. And I think that's so obvious with the idea of dark matter, because it's just so, it just reeks of a god of the gaps, grab any kind of wacky solution. I mean, it's just so invisible man. It's just so, when people start talking about drug dealers killing Nicole Simpson or something, right? I mean, it's just such a desperate effort to, make it not appear to be what it appears to be. And this is just so, it's just so fake. It's just such an extraordinary, it's like they see anything and they just make up, like they just sit there for an afternoon and just start making shit up about what it could be. And there's like very few rules about what you're allowed to make up, because no one's really going to say, well, how come you have these 4 images and by the laws of gravity they should be in all these locations too, because the gravity in these locations has to be the same as the gravity in these. And look how round they are. Like, you've got to know there's something going on here. Because, again, how could an inverse square lens create a perfectly round object? How could a lens shaped this way render a perfect proportional image? An undistorted image. How would that be possible? Alright. So again, we never see lensing from galaxies in this configuration. So, here's one here. Never see lensing around those galaxies. It's always these flat things. And that's completely opposite to what the probability should be. Much higher probability of lensing on a galaxy this way than this way. Alright. So enough. It's it's all it's a lot of technology and it's all technical. None of these images again are just images. They're all you look at this one. NASA, ESA, S. Rodney, Hopkins, Frontier Team, University of California, Kelly, California, Berkeley, Glass Team, lots of Founder Fields Team. I mean, how many people have made this image? How many groups, how many things have run this thing through their processors? And just not nearly good enough for what's stated as this is hard evidence of something, undeniable proof of something. And I think it's again, I just can't make any rational sense out of this argument. Again, how do you have this cross thing? Why at all would there be any idea of this opposite symmetry thing? Why would this line care about this line? There's absolutely no reason to ever create a cross. There's no function in gravity that would ever force a cross to happen. These two could be at any angle on the clock. You could have 6, you could have 10, you could have 1,000,000. But why you don't have them is a valid question. It's a valid question to ask. How can you have perfect objects and nothing in all the other gravity that's exactly the same gravity? How's that possible? Anyway. So anyway, it's enough. Till the next time and such. But this isn't good science. And it's tragic that we can't agree on that.